Welcome back, and here we go with 1.4, the final section of Unit 1. And this is where we're going to talk about the Big Bang and the beginning of our universe. All right, so first off, we're going to start with something about facts, theories, and laws in science, because the words get thrown around and a lot of times they're misused. So a scientific fact that is the result of a repeatable, careful observation or measurement by experimentation or other means. This is empirical evidence. A lot of times it comes with numbers. This is a fact. This is something we can see. This is something we know. Okay, it's factual. It's not up for interpretation generally. A theory. Now, this word gets misused quite often because in layman's terms, outside of science, a theory is kind of like, oh, I have this idea or I have a theory about how something works. But in science, it's actually very important. A scientific theory is an explanation of an aspect of the natural world that has been repeatedly tested and corroborated in accordance with the scientific method. When possible, theories are tested in an experiment. They don't have to be experimental. What this is saying is that all of the scientific facts that we have come together to make a theory. We take it all together and we put it all together, and then we come up with the theory, like theory of evolution, germ theory, plate tectonic theory, theory of relativity. These are all theories. Gravity is also a theory. Scientific law is a statement that describes or predicts a range of natural phenomena based on repeated experiments or observations. They are developed from data, can often be mathematical, and are based on empirical evidence. Things like Newton's laws or Kepler's laws, these are things that we see repeat over and over and over again in nature. It doesn't mean nature has to behave that way. It just means that from what we observe, it always does. And sometimes scientific laws break down at weird times, like in black holes and other times, in other weird situations. So a law, like Newton's first law, is an object that in motion stays in motion unless acted on by an outside force. That's just something that we can see in nature, and that happens to be true basically all of the time. Okay, here we go. History of the Big Bang Theory, not the TV show Big Bang. First noted in 1927 by Georges Lemaitre, or Lemaitre. It's a tough one to say, sorry. I'm not good with French. I took German. He determined an expanding universe could be traced back to a single point called the primeval atom. We call it something else now. Edwin Hubble confirmed galaxies are drifting apart in 1927 by observing something called galactic redshift. I'll talk a little bit more about redshift later, but basically we can tell that something is moving away from us because the spectral light that it gives off tends to shift towards the red end of the spectrum. Hubble's law, distance equals Hubble's law times velocity, is actually their law together in honor of both. It's named after both of them. So here we go. Here are the basics, and this is some funky stuff, but here we go. The current universe, the one we live in now, the one that exists now that's been around for over 14 billion years, began as an incredibly hot and dense point called a singularity. Where the singularity came from, we don't know. It could have come from a previous universe that collapsed. We don't really know. Maybe it's always existed. Maybe it wasn't. We don't know. Originally, that was called the primeval atom. The rapid expansion of the universe created space and time. So as this universe expanded from this one point, it created space and time itself. The term Big Bang was actually coined by a scientist who disagreed with the model. He was picking on it. He said, oh, it's a Big Bang. Well, there wasn't really any sort of explosion of sound because there wasn't any mass anywhere else except for where this thing was expanding. There was not an actual explosion. So instead, what you have is a small point that then rapidly expands, and it's been expanding since. Eventually, all matter would condense as the temperature cooled. So as the stuff spread out, it started to condense into matter. So here's the timeline. In the first small fraction of a second, gravitational force separates from the unified strong, weak, and nuclear and electromagnetic forces. These are forces we've probably taught you in other science classes. Strong nuclear holds the atom together. Weak nuclear holds particles inside the atom together as well. And electromagnetic has to do with light and radiation. So these forces were separated from gravity. Matter and antimatter. Yes, antimatter is a thing. There was matter and there was antimatter, and they collided into each other and annihilated each other. But because there is slightly more matter than there was antimatter, there's some left over. The universe has expanded enough to start cooling, and then the other fundamental forces split. This is all still within the first second. Okay, so it's still a small amount of time. Minutes after the expansion, hydrogen and helium nuclei begin to form. So the little nucleus of those particular elements started to form. And then hydrogen itself, the rest of the atom with electrons and everything, didn't start forming for another 380,000 years or so. Then over the next billion years, stars started to form and then galaxies started to form. So here's kind of another timeline. It shows basically everything I just said. And you can look at it. You can use this picture to put in your notes. You can find another one that's similar to it. But it kind of shows what the timeline was of all these things, from the expansion to, in the first whole beginning part, way over on this end, is still all within the first second until you get to right there. Okay, that's where particles were starting to form just before that first second. And then you get into the years and it expands, and we get into the present day, which is about almost 14 billion years. Okay, there's evidence supporting the theory. Hubble's law and his observations of redshift that show that the universe is expanding, that it's still getting bigger. Things are still moving away from each other. We have a thing called cosmic microwave background radiation. It's found throughout the universe. Old tube TVs used to have something called static. If you put it on a channel that wasn't there, it would have fuzz. That static is actually cosmic background radiation. It's microwave radiation. It's kind of cool. The approximate abundance of primordial elements, so different versions of helium and hydrogen and lithium, match the predicted amounts that we would think would have formed out of such an event. Galactic evolution and distribution match what would be expected. So kind of the smaller initial galaxies with larger ones forming that are newer. So the newer galaxies tend to be the bigger clusters and things, and the older ones tend to be smaller. And then there are primordial gas clouds that lack heavier elements created in star death. So these old gas clouds don't have the bigger, heavier elements that we would expect when stars blow up. And we'll talk about stars blowing up later on in the semester. Now, there are a couple problems with the theory, or questions, or things that aren't known for sure. There's something called baryon asymmetry. Why was there more matter than antimatter? Why wouldn't it be created in different, why would it be created in different amounts? Why would there still be matter left over? Dark energy. Sometimes this comes up in conversation. They talk about something called dark energy. If we could find it, it would solve some issues, because we are seeing that the expansion is actually accelerating. It's getting faster. And that seems kind of weird. That means something must be pushing it and speeding it up. Dark matter, that would also solve the issue of there being too much gravity in between galaxies. We see that there is gravity that exists between galaxies, and there's too much because there's nothing out there in between, or not much. So we're wondering if there's some sort of matter that's out there that's actually got some gravity to it. Horizon problem deals with the idea that information cannot travel faster than light, and the background radiation is isotropic. So can anything move faster than light is a big question. And the flatness problem, otherwise known as an oldness problem, states that our universe hasn't yet reached heat death or a big crunch. Eventually, because we will run out of energy. That's the way it works. Eventually, entropy means we're going to lose some energy in every conversion. And it doesn't die, but it just gets converted into something that can't be used anymore. So that's a problem. What's going to happen at the end? So there are two possible final ends for our universe. One is called the Big Chill, otherwise known as the Big Freeze or heat death. That's where the universe continues to expand and expand and expand, and eventually the energy is lost through entropy. That's something from chemistry that you may or may not remember, but when you convert from one type of energy to the other, a certain amount of it can't be used again for anything. It's still there, but it's unusable, and that's going to happen eventually. Star formation ends, all stars eventually die, temperature approaches absolute zero, and that's that. The universe is done. Or there's the big crunch. That's where that expansion will eventually slow down, and then it'll come back together. It'll reverse due to gravity. and it'll contract, and the universe will wind up back in that little teeny singularity again that exploded in the first place. The evidence shows that expansion is accelerating, so the big crunch is unlikely. Something would have to slow that down and bring it back together, and we don't know that there's anything that can. So one of these two ends is probably going to happen, but we don't know which one. So, rapid questions. Is it possible the theory is incorrect or needs revision? It's possible. Theories can be disproven or they can be tweaked when new evidence is found. So if we find new information, we can tweak them. As we learn more about quantum mechanics, could there be another explanation for the beginning of our universe? So when Ant-Man Quantumania comes out, is there something to the quantum realm? Now, I'm not saying that that's, true stuff. Obviously, that's fiction, but what is it about the quantum realm that we don't know yet? There's a lot of stuff down there that's really, 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 really small. And is it possible that a multiverse exists? Maybe, it's possible there are many, many, many universes. They all exist at the same time. We don't know. So those are things that science is still working on. All right, that's it for this one.